All right, ladies and gentlemen, class recording is started. So, on Friday, we introduced the concept of energy, and we talked about that energy is our ability to do damage, or the ability to make things different, change things. And so, yesterday, we talked about a specific type of energy, we talked about kinetic energy, and we looked at how the mass and the velocity of an object affects its energy, right? Where mass is a direct relationship, mass is directly related to the kinetic energy, but velocity is quadratically related to the energy. And then we also introduced the idea of potential energy. If kinetic energy is energy of motion, right? Yesterday when we introduced potential energy, I introduced it as energy of position or location. If kinetic energy is the ability to do damage because something is moving, potential energy is the ability to do damage because of where it is. And so, all right, the result, energy of position or location. And so yesterday we introduced gravitational potential energy, which we represent with the notation PE sub G, right, for potential energy gravitational, right? Potential energy that depends on the location of an object from the ground or some source of gravity. And we said that the potential energy of an object depends on three things. It depends on that object's mass, it depends on how far away it is from the source of gravity, and then it depends on the acceleration of gravity at that location. All right? Good there? We okay with that? Did we get through this calculation yesterday? I can't remember. Oh, the units? Okay. So, just to recap, right? It's asking us what is the gravitational potential energy. So, like we said, PEG is equal to M times G times H, right? And then it told us that the mass of the book is 1.5 kilograms, so that goes here. We know that here on Earth, the acceleration of gravity is 9.81 meters over second squared, and then, right, 2 meters above the ground, plugs in there, and then what did we get as far as the value, or the magnitude of this gravitational potential energy? Can't remember. Frank, good. 29.43? Okay. So 29.43, and then we had to round it to how many sig digs? 2, so we round that to 29 here, all right? Units, right? Units. Because we're multiplying, we just multiply all of it together. So, kilograms times meters over second squared times meters, right? But if we simplify that, we get that, yes. Okay. And yesterday, right, when we were doing our kinetic energy problems, we said that that combination of units, right, kilograms times meters squared over second squared, that's what we represent with joules. And so here, even though we got to it a different way, if we have that same combination of units, we use joules to represent that. Good there? And finally, like I said, oh, I don't think I told you guys this yesterday, but I did tell the other class this. I'm not doing these examples because I don't think that you guys can plug numbers into an equation and solve for it. But especially with this kind of problem, rearranging that equation to see how the different factors affect the result is something that shows up a lot, like on standardized tests, SATs, ACTs, AP exams, IB exams. So I want to get you guys in the habit of looking not just at the numbers that go into the equation, but the relationships that are there, because a lot of times those questions show up where they're just looking at factors and not actual numbers. So that's why I'm doing this for you here, right? So it says, find the mass of the ball find the mass of a ball on a roof 30 meters high if the ball's gravitational potential energy is 58.8 joules. So, we know that gravitational potential energy depends on those three things, right? But this question is asking us to solve for what? Mass, right? Now, we can plug numbers into this equation and find the mass, and that's fine. But before we do that, I'm going to rearrange that equation just like that. Okay? Here's good.
You don't have to.
No, like I said, you don't have to. But here's something that I kind of want to show you, right? So I'm going to use a different color to show you that this is not related to this problem. Okay? Okay. So you guys don't have to write down this blue, but this is kind of the point I'm trying to make with this. Okay? Here, I rearranged the potential energy formula to show you, just to solve for H, right? Okay. So now we have height over here, and we have gravitational potential energy over here, all right? On two sides of the equation, same thing as up there before, right? But if we make height like twice as big, right? If we take it to a second-story window from a first-story window, we make it twice as high. If this side of the equation goes up by 2, what has to happen to that side of the equation? It has to go up by 2 as well. And we can see that here by having them on different sides of the equation. Yeah, they're on different sides of the equations over there. That's fine, right? But, again, a lot of times when we look at, like I said, this shows up a lot with multiple choice questions on standardized tests, where they want you to just look at variable relationships without actual numbers. And so manipulating these equations without subbing numbers into them first is an important skill to have to handle those kinds of questions. Does that make sense? Could you plug in the numbers first and then solve for them? Yep, you could, but I want you to get into this habit a little bit more as we go along, okay? All right. All right, good there? Just plug in the numbers. All right. 294.3. Are you sure? 294.3? Seems kind of high. Say again? I think you already did that. No. What'd you get for the whole thing?
Oh, 0.2.
Okay. So. Okay. Like that? Okay. So, first, everybody get that when they plugged it into their calculator? Did anybody else plug it into their calculator besides Frank? Oh, that's okay. That would be good practice. Okay. Either way, that's going to end up the same thing. So, Frank, do I need to run this through my calculator, Frank?
I got the same.
Oh, you got the same thing, Frank? Okay, so. I'll check and make sure if you plug the numbers in properly. So. Okay. All right. So we got this right here with this equation, right? From sig dig's standpoint, how many sig digs does our answer have to have?
2. No, 1.
1. Okay. Maddie, why 1? Good. Good. So 30 has the least number of significant digits because it only has how many significant digits, Maddie? Just 1. So what are we going to round our final answer to? 0.2. All right. Now, say again. Nope. Because where's this 0 at? Beginning zeros are not significant, right? Regardless of whether the decimal point is there or not. So, now, unit-wise, just knowing what we should know, what unit should we end up with in this problem? Kilograms, right? That's our unit for mass. So, we have joules on the top, and meters per second squared and meters on the bottom, right? Do you remember the combination that makes up joules? We just talked about it, right? Here, this is really kilograms times meters squared over seconds squared. So that's the combination of units that shows up on the top, right? On the bottom, we have meters over seconds squared and meters, right? If we multiply the two things on the bottom together, we end up with that, right? And then what's going to happen top and bottom of this equation? These are going to cancel, right? Boom, boom. And now the only unit we have left with is what? Kilograms. And that's what we should end up with, right? So that's what we see. While joules is the unit for energy, right? Even if we're not solving for energy, we're still going to end up with the unit that we're supposed to end up with, as long as all of our other units are where they're supposed to be. Good there? Okay. Let's transition back to the outline that we've been working on for the past couple days. About, oh, that's not the right one.
Is that a test?
That's your quiz. So if you go back and look at it real quick, there'll be like a couple questions on there, unless I change them on here. Well, no. Your quizzes that you do in Google Form, like that's my paper quiz that I gave last year. I just put it into Google Forms. So. Yeah, first year I've done Google Form quiz. So. I think it's going pretty well. Do you guys like being able to?
I like it.
Well, one thing for me, it doesn't take class time to do. Like you guys do it for homework, and so that's kind of nice. But also grading wise, it actually goes pretty well for me. I'm pretty happy with it. So yeah.
Did you do open no last year?
Yeah, if they were open no quiz, they were just on paper instead of doing it for homework. So. All right. So we talked about energy. We talked about kinetic energy. We talked about potential energy, and then specifically we talked about gravitational potential energy. There's one other type of potential energy that we will talk about that we won't do calculations with. We'll just talk about it conceptually, and that is elastic potential energy. All right? So elastic potential energy, PE sub E, which I think is at the bottom of the first side of the outline. Okay. So potential energy that results from something being stretched or compressed. So when we talk about potential energy being the location or position of something, the location or position that we're talking about with elastic potential energy is how much have we stretched or compressed some kind of a spring or an elastic band or a rubber band or something like that. All right? Again, it's energy of position in that we're stretching it more or less, and that results in its ability to do stuff, right? We've all done, like we have this rubber band, right? If we want to snap our friend with it, we can either stretch it this far and then snap them, right? Or we can stretch it this far and snap them, right? The farther we stretch it, the greater position that's involved with this rubber band, the more energy, the more ability it can do stuff. Does that make sense? Okay with that? All right. Next topic. Flip over to the back side. Let's talk about work. Work and energy are two topics that go together all the time, and a lot of times they are introduced together, and there's a reason why that is. So we talk about energy, the ability to do stuff. But what we look at in real world situations is having that ability to do stuff, but then transferring it to somewhere else to actually do the stuff. All right? Does that kind of make sense? I know that's not real scientific, all right? But when we look at a situation, we follow the flow of energy, and that tells us what happens. So we got to talk about the flow of energy. Where does it go? How much of it goes from this object to that object, and what happens because of it? And that's where work comes in. By definition, work is the transfer of energy between objects. transfer of energy between objects. And that means that when work is being done, we will see the energy of an object change. All right, the energy of an object will change when work is done, because that's what work is. It's a transfer of that ability from one thing to another. Yes, Frank? What is the definition of work there in chapter 15? Let's talk, that's more of how we calculate the amount of work. This is come from a conceptual standpoint, okay? We'll get there in a second, all right? So, when we talk about work, we're talking about the change in energy. Now, if we talk about this baseball, okay? It can have kinetic energy. Does it have kinetic energy right now? It's not moving, right? It might have some gravitational potential energy because it's off the ground, but it doesn't have kinetic energy. What has to happen in order for this ball to have kinetic energy? It has to move, right? It has to start moving. What do I have to do to it to get it to start moving? Apply a force, right? So work depends on force. If we're going to transfer the energy from one object to another, the force is what transfers that energy. So, when we're determining how much work is done, we have to look at two things. We have to look at the force that is being applied, and then how far that object moves because of our force. So work is only done if a force is applied and the object's motion changes because of that force. Both of those things have to occur in order for work to be done. And when we calculate how much work is done, we multiply those two factors together. So work is equal to force times distance, or W is equal to F times D. And that's letter D on your outline. A lot of our discussion about work in this section is going to be conceptual. All right? So you'll see that on your outline down there, there are a sequence of 4 pictures. I'm going to show you the same 4 pictures, and the same question is going to show up each time. And that question is it work? All right? So, first situation. Is it work when a pitcher throws a baseball? Yes. All right? There are 2 ways that we can explain that this is work. I really felt like I had to sneeze, and then I went to go sneeze, and then it was fine. So. All right. So, is it work? Answer, yes. So let's talk about 2 ways that we can justify that work is being done. What's one way that you can justify that work is being done if a pitcher throws a baseball? Good. You're on the right track, but we didn't say it properly. What happens to the kinetic energy of the ball because of what the pitcher is doing to it? Okay, what happens to the kinetic energy of the ball because of what the pitcher is doing to it? Okay, the ball goes faster, right? What does that do to its kinetic energy? It increases it. Good. So, the kinetic energy of the ball increases because of what the pitcher is doing to it. That's one way that we can justify that work is being done. Right? What's the other way that we can justify that work is being done? Look at your definition right above this picture. There is a change in motion because of what? Because a force is applied, right? So, is this work? Yes. The ball has more kinetic energy because of that applied force. Because the pitcher applies a force to the ball then gains kinetic energy because of that force. So yes, this is work. Okay? Good there? We also could explain it by saying that the pitcher applies a force and the object moves because of that force. Force times distance is work as well. Either one of those ways would be fine to explain it. Okay? Good there? All right. Is it work when this girl uses a pulley to raise this box up to the top of the platform that she's standing on? Is this work? Yes. How are we going to explain that this is work? Force is applied, and then does the box move because of that force? Yes, it does. How else could we explain that work is being done here? Potential energy is increasing because of what she's doing, right? So, is this work? Yeah, this is work. The crate has more gravitational potential energy because of that applied force. Good so far? Alright, good so far? Joe's good, everybody else good? Alright, so let's talk about another frustrating situation that I'm sure a lot of you have probably dealt with before, right? So I know that a lot of you probably go home and, just to like have some release, right? You sculpt out of like your marble, you just get a big block of marble and like, chisel it out and, I'm sure that's how a lot of you spend your time, right? I mean, but sometimes, that big block of marble just isn't where you want it, right? So you want to move it over to that spot over there. So again, because you don't have a dolly or a cart, you just have to lasso that bad boy, right? But you pull like really, really, really hard on your block of marble, and it doesn't go anywhere, right? Is that work? No. Are you working hard? Yes, but is it work by the definition of work? No. Two ways that we can justify that. Frank, what's one way? The marble's motion does not change. There is no distance in the force times distance. What else can we say? It has no kinetic energy, but more importantly, did it have any kinetic energy before we started? No, and it has no kinetic energy now. So did its energy change? No. That's the important part. Does that make sense to you? It's the change in energy. So, two ways. One, and you can use both of these definitions, or just one, right? The marble has no more energy because of that applied force. Or, there's a force applied, but there is no movement, right? So if we look at our definition, our equation for work, F times D, if we apply a force and it doesn't go anywhere, that's not work, all right? So two ways that we can explain that this is not work when we apply a force to something and it doesn't move. One, no change in energy. Two, doesn't go anywhere. D is 0. Okay? Good there? Okay with that? So, a lot of times you need this release when you get home because you've had a stressful trip home. Because I know that this happens a lot as well here in Westlake, right? That you're on your way home and boulders just start rolling down the hills, right? And they're chasing you, right? So here, right, you run away from this boulder. You don't have to run forever though, right? Eventually what's going to happen to the boulder? It's going to stop, right? Is work being done as the boulder is stopping? Yes. All right. What does work do?
Work is being done because the force of friction is applied and friction changes motion.
Okay, so there is a force being applied in this situation. It's friction. And does friction change the motion of that object? Yes, it does. If we think about it from an energy standpoint, right? What's happening to the energy of this boulder as it rolls along the ground? Good. It decreases, right? How fast does it go as it rolls along the ground? Or it slows down, slows down, slows down. So is its energy changing? Yes. But what's specifically happening to its energy? It's decreasing. So what do you think we call that? Work so far has only increased the energy of the object, but we can also have work that decreases energy. And we distinguish those two, right? Okay? So, is work being done here? Yes. That boulder has less kinetic energy because of the applied force. And so we say that there is negative work being done. All right. Now, I'm going to ask you to do some brain work here. Okay? I know that's disappointing, but I'm going to ask you to think. Sorry, I'll let everybody finish because I want you guys to really consider this. Okay? All right. Up until now, when we throw a negative into something, what is that representing? Opposite direction. But that applies when we have what type of measurements or what type of quantities? Vector quantities, okay? Work is not a vector quantity. Work is scalar. Up until this point, we never had scalar quantities that were negative. Like distance, right? Distance is always positive, right? Time is always positive. Here, we have a scalar quantity, but I'm describing it as negative, right? It doesn't mean direction in this case. If I describe this scalar quantity as negative, what's happening? Okay, that's true. It's negative force, and that causes negative work, but that's not what I asked you. If I call this scalar quantity negative, what is that representing? What does a scalar quantity tell us? Only magnitude, only how much. So, if I'm saying the how much is negative, what does that mean? What's happening to how much of what we have? It's decreasing, all right? Here, with negative work, we are seeing a decrease in the magnitude of the energy, okay? So like I said, I make this point, not because I'm trying to confuse you, even if you may come out of this confused, but we can't always assume that scalar quantities are positive. Sorry, get those for emphasis. Right? We can't always assume that scalar quantities are positive. Scalar quantities can be negative. Negative scalar quantities just means a decrease in magnitude. It's smaller than it was before. All right? So don't fall into that trap that scalar quantities are always positive. It's not always true. Okay? We okay with this definition of work? All right. To wrap up today, let's take a look at the sheet that I gave you that says 14.1 work and power. Okay. So on the front page of this sheet, right, we start off and there's a pretty simple section, or a pretty short section on work, right? And it says, work is the product of force and distance, or F times D, which we already introduced to you. Conceptually, we learned that work is a change in the energy. But a lot of times when we look at measuring work, we're not only concerned about how much the energy changes, but how quickly the energy changes. And that gets us into power. As you can see here on the front page, the first sentence right here, power is the rate of doing work. We've discussed previously, when we describe something as a rate, what does that mean? What factor are we ultimately looking at as well? Time. So, if power is the rate of doing work, we calculate power by taking the amount of work that we do and divide it by the time over which that work occurs. So now, we're not just looking at how much does the energy change, but we're looking at how quickly does the energy change. Okay? So let's take a look at page 3 of that packet, and let's look at example number 2. Exercise 2, sorry. So exercise 2 says, a man exerts 700 newtons of force to move a piece of furniture 4 meters. If it takes him 2 seconds to move the furniture, how much power does it require? So we just learned, right? Power is the rate at which work is done. So power is equal to work over time. But earlier in the day, earlier in the period, we learned that to calculate the amount of work that's done, what do you need to know? Distance and force. So this equation, we can modify. We can modify to look like this. Does that make sense? So now we have the formula that takes into account the information that we were given in the problem, right? How much force is applied in this situation? 700 newtons, so that's going to go here. It was moved how far? 4 meters, so that's going to go here. How long did that take? 2 seconds. All right? And so we plug that in, and we should end up with 1,400, if I'm not mistaken, right? So 1,400, okay? Now, right, if we look at units, we have, and I'm just going to do this up here, newtons, meters, seconds. All right? That make sense? I can get this done. So, newtons is a derived unit. It looks like this. Okay? Sorry. Forgot one. Right? You see where that's going now? Okay? what are we going to end up with on the top? That's joules, right? Kilograms times meters squared over seconds squared, joules over seconds, okay? That's our unit for power, but this is another derived unit. That is the watts, all right? We'll do a couple more power examples, and then we'll talk about conservation of energy tomorrow.